the torsion
The
and
normal
you
closure.
are full
Right, so I
backs.
could just, you know.
Yeah, that's
So S was the normal closure.
Just give
Of
us the main
G.
characters.
T was the normal closure of Y in H.
Like
What's
Shakespeare
P?
class.
Yeah, just tell us
Yeah.
who Hamlet.
You know,
Mercutio.
But
P is
just
the
as like S,
torsion.
yeah, P
is
mod
the
Q,
torsion.
yes. P mod S1 is the torsion subgroup of S mod
I
S1.
thought S and T were the torsions.
Write it down, Anthony,
Well,
for us, please.
I beg of you.
so before, look, it's
don't just
So I'm
write
saying that
what P was.
P, this is the torsion
That was torsion.
Okay.
Of
subgroup,
G minus.
Torsion.
S mod S1.
Yeah.
Okay, because S mod S1, it's the abelian, you know, it may have torsion, so we want to kill the torsion subgroup. So we mod it off, which means that by the third isomorphism theorem, this gives rise to S mod. So which means this is the torsion subgroup this, which means that this gives rise to S mod P. Okay, so we take this modulo this, we get S mod P, which would be torsion-free abelian. Okay, so a lot is going to, you have to keep track. It's not that easy to just see this, but you have to spend some time to
Meditate.
yes, keep track of it. It's very condensed in what I'm doing. So because this, we can represent this as a semi-direct product, it means that we can take powers of, because we, remember what G was. G was S, the semi-direct product of S by the infinite simply group on A. The same thing occurs here, which means that we can take elements of this by times this, yes? Because that's the form of a semi-direct product. So it has this particular form. Now moreover, this relation holds in L. Now remember, which means that we can have A, B,
L. So L is G mod P.
yes. So why does it hold in L? Well, first of all, the subscript. What was, remember the S was the subscripts of the B's, yes? So S mod P has B subscripts in it. So we have to also show this also holds in L. This relation holds in L. So it means that a typical element of this B sharp, which is this, I just put the notation B prime. So B prime has this particular word. And what is the word? B I1 prime to the epsilon 1, where epsilon, these are two words, plus or minus 1. And so with some very elementary
You liar.
form, we see,
Oh.
Now it's clear.
now it's clear.
It was not.
Now the BI commutes, yes, because we are dealing with a torsion-free abelian subgroup. So this is true. Now similarly, we can do the same thing for H. Okay? And the same thing holds that H is equal to T by the cyclic group X generated by X. And the same thing follows. So again, just as we did for B, this is just like a corresponding thing we can do for H. So the idea here is that T mod Q is torsion-free abelian. Okay?
Can I just ask one question? Maybe I'm going way back. Is it clear that S1 is included in P?
Remember,
No?
I just said let this be P mod S1.
Yeah,
Let,
So P includes S1?
yeah.
yes.
He's defining it.
Because
I'm
you are
defining it this way,
pulling
that I
back
want to just kill the
S1 is
torsion.
P.
So P mod S1 is a torsion subgroup of S mod S1. Okay?
So when we
So
look
P-
at S mod P,
P is a subgroup of
where-
S.
It's
where
torsion-free, yes,
automatically
it's torsion-free abelian. So now I can continue with the same thing for H. H we can have this holds in M because, and we could invoke lemma 3. L is G mod P, M is H mod Q. And so, remember what Phi was, Phi star was. So Phi star mod L into M. Remember what Phi star was? Phi star mod G mod P into H mod Q. So, nicely, this works out very nicely in terms of notation. So, we look at the quotient of this, L mod B sharp. So again, L is G mod P, and we mod it out by B sharp. What was B sharp? S mod P. So we see that L mod B sharp, this is isomorphic to G mod
Yes.
S. Ah. So we just have, now this isomorphism is just take the one generator to the other generator. So we're going to look at specific words under the induced isomorphism and see where it's, where the target, where it goes in the target. And so what happens here is that I call it,
Is that a vector?
yeah, well, no. I call it just an arrow, so now I'll just make it the arrow. I will just call it bar instead of arrow. So we take this element, this is the quotient representative. I call it is A double prime B sharp. And because that's equal to phi of A double prime times Y sharp. Remember, phi sharp takes B sharp into Y sharp. So under this particular, which is a homomorphism, so we can, this is true. Now, if we look at where it goes, either this takes it to the target, the generator, X double prime, or its inverse. Yes, because it's infinite cyclic. You just take 1 to 1 or its inverse. So we could just look at the first case, just where it takes A double prime to X double prime. And it turns out that this is in Y sharp, so this element is in Y sharp. So if we multiply by, which means that the small Y sharp is an element of Y sharp, which means that if we multiply by, on the left, by X double prime, we get phi star of A is equal to X double prime Y sharp. And that is uniquely determined because this is exactly what it takes it to. So what do we want to look at here? Well, that turns out, we see that as a result of this, we can also look at
Very lovely.
so this is very
It's so beautiful.
so
Next slide.
I was wondering if to include
Next slide.
these details, but I could just wave my hand and say hence. But I just decided to show you that
He can give us a break.
so you could just read this.
It's getting hot.
And just,
Give us 5 minutes here.
so that's what I'm saying. A lot of things, it's very condensed, and so I had like 20-something pages of this, and I shrink it to like 5. So it's
Single space.
So Sal just mentioned that for torsion radiator group, it's solvable isomorphism problems.
They are hyperbolic. If they are hyperbolic, and they are hyperbolic.
So can you prove for torsion Baumslag Solitar group just the same thing will go through? If you have the torsion.
no, there's well, if you take element of
Yeah.
to
I
some
mean,
power.
No,
For torsion, I mean you take Bn to the other side and take it to some power t.
Yeah. So then the relator isn't provided.
Co-provided, yes, yes. I even was thinking about that, yes. So this is probably an next yes.
I'm sorry, what happened?
I'm saying that you don't necessarily have to take the relation, but I'm saying that because the relation is so nice, and I want to look at the isomorphism, the infinite cyclic one, when I take...
You know what he's playing on is really a local
The-
indicability condition.
Okay.
because that's
Because
really what happens there.
I'm using
And I'm
this
not
here
sure
as-
how that plays out with the
as
torsion
the
body later.
the nice way to do this. So, but we can follow
I think
this.
so.
The BMN.
I think so, but I'm
So
not
let me
sure.
just read this. So notice what we have. We just look at the image under the star. So again, it's an isomorphism, so it's a homomorphism, so it will be phi of A double prime inverse, phi star of B prime and to the M.
Yep.
Yes?
Yes.
Now, we know exactly from previous where B star takes B prime, yes? It's
Tell us.
X double prime. X double prime, yes?
Yes.
So, all we can, once we do this, we see that the image X double prime times some element in Y. Because that was, so we just replace the image on the phi star of A double prime to be X double prime small Y sharp. That's what we got before from the previous. And we do the same thing for the B prime to the M. This is just B prime, this goes to Y prime, some element in Y. And we see that the phi star restricted to B is actually phi sharp. Okay? So, continuing, phi sharp takes B sharp to Y sharp, leading to this particular equation, which leads to this particular equation. So the image under this particular word, we have on the phi star, we end up with this word. But this is the same typical element in H, just as how we start off with the B's. So notice now we have two equations. One in terms of this, we can just take the nth prime of this, and then we can take the n prime of the other one. So we just take the n prime of this relation, and because the y commutes just like the b's, we can shift things around. And it turns out that we have this relation, which implies that we can compare the powers of the y. And it turns out that when we do that, we get n times n prime is equal to n prime times m. Well, this will be the next slide. So we get the next relation in terms of the n prime, and the n prime and m. So remember from the original we have n minus m is equal to n prime minus m prime. This also holds. So this implies that n squared minus n times m is equal to n times n prime minus n times m prime.
Can you remind me of something? The y prime, that lives in a torsion-free.
Correct,
That's
exactly.
why that
Yeah.
equals.
That's why, yes.
Yeah.
We can take
Otherwise
power
it's
so it
all.
doesn't go to 1. And we factor, very elementary. Now, and
Factor n prime.
since n minus n is not 0,
N on the left.
That's
Exactly.
the expression.
and since n minus n is not 0 because we take it to be greater than 0, it turns out that n equal to n prime. This is true, hence m is equal to m prime.
That's where you really use
So after
that.
some hard work,
And
we finally
equal.
Are happy.
happy, yes. So yeah, so it's involved some more.
How many pages is it proof? 20, you said?
No, I started with 20, but this is 5.
Okay.
Okay, so this is one of the papers that will be published later on this month, I guess, or this fall.
How many papers did you get out of your thesis? How many papers did you get out of your thesis?
Well, I'm not sure as yet. This is one. I'm working on 2 more, actually.
Good.
So there's other conjecture that I have there as well about certain isomorphism problem for amalgamated products of these type of groups,
Huh.
which really get crazy. I mean,
Mhm.
this is even complicated. Imagine you're taking these and you amalgamating them.
What happens?
Where you
here?
got
Well,
this,
you really don't know, because when you